and welcome to this lecture. We are in week 3. We are looking at the joint PMF of two random variables. We are studying two random variables together in a probability space. What are all the different types of distributions that are of interest? Okay, so we saw the joint PMF. Now we are going to look at what are called marginal PMFs when you look at multiple random variables. This word marginal will show up a lot, and it's very important to understand what marginal is, what marginalization is. Okay, so there's also this word called marginalization. You'll hear a lot when you study probability and statistics. It's important to know where it comes from. Okay, so let's first define marginal PMF. It's not actually a major definition, but you'll see it's easy to think of. So I'm going to start with two jointly distributed random variables. So let's say x and y have a joint PMF fxy. Okay, so the PMF of the individual random variables, right? So you're given a joint PMF. Let's say you don't start with the marginal PMF. You start with the joint PMF. You don't start with the individual random variables. You start with the joint distribution of two random variables. Somebody gives you the table. Okay, how do you go from there to thinking of x as an individual random variable? Okay, so x is a random variable on its own. Y is a random variable on its own. Each of them have their own PMFs. Those kind of PMFs, when you have joint distributions, those individual PMFs are called marginal PMFs. Okay, that's just a notation or a definition in some sense. It's a very simple definition. But the important thing are these two equations. These are marginalization equations. Okay, what is marginalization? You have the joint PMF. How do you go to the marginal PMF from the joint PMFs? It turns out this way is uniquely defined by these specific equations. Remember once again, from the joint PMF, you have a clear equation which will take you to one marginal PMF. Nothing else is possible, and that's given by this. Okay, actually it's very easy to prove this. Let's look at the first statement, fx of t, right? What is fx of t? It's the probability that x equals t, isn't it? Now what is, let's go down to the proof here and see what is x equals t. If you look at the event x equals t, one can write this event as x equals t and y equals y1. So let's say the range of y is y1, y2 to y sub capital K. Okay, some k entries are there. So if you want to just think of x equals t, I can always write this event as x equals t and y equals y1, or x equals t and y equals y2, so on till x equals t and y equals yk. This is a way for me to decompose this x equals t as a disjoint union of several events, right? So this is something we have done several times before, right? Now, once you do this, probability of x equals t, now these are all ORs, but even though they are ORs, they are all disjoint, isn't it? Y takes different values, so they are all disjoint. So when you write probability of x equals t, it's probability of x equals t comma y equals y1 plus so on till probability of x equals t comma y equals yk. And that's what's written here. Okay, so notice how this goes to this exact same thing. Sum over all the values in ty in the range of y, fxy of t comma t prime. So you take the value of x, okay, the value of x is fixed to t throughout, and then you take all possible values for y and simply add the joint PMF at all possible values for y with the same value of x. So that process is called marginalization. Okay, so here in the first equation, you are marginalizing y. Okay, so you're marginalizing y out of the summation. So you're only left with x. Okay, that's what happens. Now very similarly, you can do fy of t. The same proof will go through, but in this case, you'll have to marginalize out x. Okay, so sum over all t prime in tx, the joint PMF t prime comma t. So you keep y fixed at t, go through all possible values for tx and add up the joint PMF, you will get the marginal PMF. Now the marginal PMF is so uniquely defined once you define the joint PMF. Okay, it's simply a PMF, it has its own range, and you can calculate from the joint PMF, okay, through this marginalization process. So let's see a few examples to see how marginalization works. It's easiest to think of the table and do the marginalization with respect to the table. So in the toss a fair coin twice example that we saw just a little while ago, we had this table for the joint PMF, right? 1 by 4, 1 by 4, 1 by 4, 1 by 4. If you want to do the marginal PMF of x1, you simply add over the columns of joint PMF table, right. So, if you want to do fx1 of T1, okay, T1 is 0, 1, I want to do fx1 of T1, right. So, this is fx1 of 0, this is fx1 of 1, okay. So, you simply add along the column. So, you add these two, you get this guy, you add these two, you get this. This is how you marginalize, and then likewise you add along the row, you will get fx2 of T2. Okay, so 1 by 4 plus 1 by 4 is 1 by 2, 1 by 4 plus 1 by 4 is 1 by 2, like that. Okay, so once you write down a table, joint PMF is written as a table. How do you marginalize? If you just sum over either the rows or the columns. Okay, the values that vary as you go over the rows are basically T1, isn't it? If you write T1 there, so T1 comes from x1, so you will get the marginal of x2, the marginal PMF x2, as you add up everything in the row. If you add up everything in the column, you will get the marginal PMF of x1. Okay, whatever doesn't change, whatever remains the same, you get the marginal PMF of that. Okay, so it's simple, isn't it? You just write down the table, add up along the rows, add up along the columns, you get the marginal PMF. So once again, remember, given the joint PMF, the marginal is unique. There is nothing you can do to change the marginal PMF. You will just get one value for the marginal PMFs, okay, given the joint PMF. Okay, so let's take a slightly different example. So let me just show this to you. You've got here, so if first anybody gives you a table, you can verify that this is a valid PMF. Verify, it's a valid PMF. Okay, how do I verify that? You can see every entry is between 0 and 1, that's easy enough, and you can add all these guys. This is equal to 1. Okay, so it's a valid PMF, no problem. Okay, once you know it's a valid PMF, it's just a question of adding along the rows, adding along the columns. You're going to get here 0.40, 0.60, you're going to get here 0.30, 0.70. Okay, so you got your PMF for x2 here, you got your PMF for x1 here. Remember, this has to be a valid PMF, this has to be a valid PMF, all of that you can check. You can check that this is a valid joint PMF. Okay, you can check that this guy is a valid PMF, 0.4 plus 0.6 is 1. You can check that fx1 of T1 is a valid PMF, 0.3 plus 0.7 is 1. Everything works out very cleanly. You get marginal PMFs so easily here. Okay, so you see, I mean, given any table like this, you can also add it up and find out. It's no big deal, it's very easy. Now, I want to quickly point out that the same marginal PMF can result from different joint PMFs. Okay, in fact, you can have any number of joint PMFs giving you the same marginal PMF. So, this is a mistake that most commonly a lot of people make. Okay, what a lot of people will assume is, given the marginal PMF, they will simply assume that the joint PMF is the product of the marginal PMFs, and you will get some value for the joint PMF. That's a valid answer, right? Given the marginal PMF, that is one way to come up with the joint PMF, but that's not the only joint PMF which will give you the marginals. Okay, so I've shown you here case 1 and case 2. In case 1, you see the 1 by 4, 1 by 4, 1 by 4, 1 by 4 distribution is there, and you got a marginal half, 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 half. Okay, very easy. Here, look at case 2. The joint PMF is something else. I put a variable x here between 0 and 1 by 2. Okay, maybe you want to take that variable to be, I don't know, you take it as, don't take it as 1 by 4, take it as something else, like 1 by 10 or something. Okay, maybe you take it as 0.1. So, you have your 0.1, here you have 0.5 minus 0.1, which is 0.4, here again you have 0.4, and here again you have 0.1. Okay. So, clearly this is different from this joint PMF, right? This is all 0.25, here you have 0.1, 0.4, 0.4, 0.1. But you find the marginals, you will get the same marginal, okay, half, 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 half. So, notice what has happened here. So, remember this rule, this is very, very important. You can go from joint PMF to marginal in a unique way. You cannot go from marginal to joint PMF in a unique way. Usually it never really happens. I mean, you have to really cook up a very strange situation, very simple, trivial sort of situation. Only then you will go to the unique joint PMF. Otherwise, always given the marginal alone, there can be any number, usually an infinite number of joint PMFs are possible, giving you the same marginal PMF. Okay, so this is something important to understand, and know that one way is definitely unique, the other way is not unique at all. You can get any number of joint PMFs if you only want a certain marginal PMF. So keep this in mind. I know already this is a slightly different idea to keep in mind, but just by the way in which we added, you can see that it can all work out and still you can have. So notice this is a valid PMF, right? For any x between 0 and half, this is a valid PMF. Okay. So 0, you add up all this, you will get half plus half, which is 1. Okay. So it's all interesting cases you can have. So in fact, you can push it to the extreme. You can say, x is 0. If you set x as 0, you will get 0, 0, half, half. That also has the marginal of half, 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 half. Marginally, it will all look the same. Okay, but joint, look at how different it is. It is half, half here, 0, 0 here. While you have 1 by 4, 1 by 4, 1 by 4, 1 by 4. Very different sort of joint PMFs that give you the same marginals. Okay, so this is also important in practice. Okay, so whether you have something tending towards the independent case, which is 1 by 4, 1 by 4, 1 by 4, 1 by 4, or something else is something you have to look at very carefully. Okay. All right. So let's move on. Okay. So let's go back to this random 2-digit number example. You remember the joint PMF that we had, right? With this 1 by 20, 1 by 20 occurring alternatively. Okay. So here again you can add to get Fy of T2 and Fx of T1. Okay. And you see, you get what's expected. You get 1 by 4, 1 by 4, 1 by 4, 1 by 4, and 1 by 10, 1 by 10. We knew this before, right? We knew that x is uniform. 0, 1 to 9, and then y is uniform. 0, 1, 2, 3. We knew these two before. And we knew that x and y can sort of influence each other. It's not like so notice what's happening here. So if you look at probability that x equals 0, comma y equals 0. I want you to think about this. This is basically what? This is probability that x is equal to 0 and y is equal to 0. Okay, and this will work out to 1 by 20, right? Now, what is probability that x equals 0 times probability that y equals 0? So, probability that x equals 0 is 1 by 10, isn't it? Probability that y equals 0 is 1 by 4, isn't it? So, you get 1 by 40. Okay. So, these two you see are not equal. So, clearly, x equals 0 and y equals 0 are two different events that we have defined using the random variable x and y, and they are not independent. Okay, you can see that the product of the two probabilities is not the same as the probability of the intersection of the two events, right? So product is not the same, so these are not independent. Okay, so notice how from the joint PMF you can find the marginals and you can determine independence of events defined using the random variables. Okay, so this is an important process. So quite often you may define a joint PMF and then say, is this event independent of that event? You can calculate that from the joint PMF, right? Find the marginals, find the probabilities which they are defined with x and y. So basically find the individual probabilities of the two events and find the intersection of the two events, see if the product is satisfied. Okay, so these kind of things you can do with the joint PMF. So the joint PMF is a powerful tool. It gives you all the data that you need to work out any problem with the two random variables.